So now that we know what the conditional formation constant is in an EDTA complexation reaction, let's put it to use on a simple example. And this example is not totally realistic because there's information here that you're not always going to have access to, but it'll help, I think, reinforce the concept of what it is before we employ it in more nuanced ways. And so the example here is for the complexation of calcium 2 plus in solution using EDTA. And so by convention, as always, we're going to use the Y4 minus ion as we draft our equilibria instead of writing all of them up. So that's what I have in blue to the left. I have calcium 2 plus Y4 minus forms the calcium Y2 minus complex. And that's dictated by the equilibrium formation constant Kf here, or K prime F, if we adjust that for the concentration or the fraction of Y4 minus at different pHs. And what we're being asked to find is the free calcium concentration. And when I write that as calcium 2 plus free, I mean the unbound, meaning it's just floating around solution, even though there's EDTA present in solution. And we want to do that at a pH of 10 and 6 when we know the concentration of calcium Y2 minus is 0.1 molar. We're going to need a couple other pieces of information here from these tables. You'll always have access to these tables. So we need to find calcium in our table here. It's pretty small. I don't know if you can read that, but it's right here. You also have access to this in your book. The log Kf value, and I'll just put that here, log Kf for calcium is 10.65, which means that the actual Kf, uncorrected, this is not the conditional Kf, just the Kf, that's equal to 10 to the 10.65. So massive formation constant, so we know that this thing is going to go to completion for sure. The other piece of information, or couple pieces of information we need, are the fraction of Y4 minus at these two pHs, 10 and 6. And so we've got a pH of 6 here. That gives us a value of 1.8 times 10 to the minus 5, and 10 is 0.3. So I'll write these two things up here too. So alpha Y4 minus at 6 is 1.8 times 10 to the minus 5, and the fraction Y4 minus at 10 is 0.30. Okay, so I'll extend this line a little bit here. This is all our sort of constant information that we need to solve this. So this problem is worded a little strangely and may not be totally intuitive, and that's fine because I'm not going to ask you a problem like this. This is just illustrative of the process to help us understand. If we know that the concentration of this thing is the 0.1, what we're really assuming is that's a formal concentration of the complex. And so in other words, what we're really assuming is we have a system where we're adding the complex version to water, and we're allowing that to equilibrate, and that's how we're going to compute the concentrations of the remaining species. And so we can write that up like we have it currently, but it's going to look a little backwards here. So we can write up sort of an IE table here where the initial concentration of calcium and Y4 minus are essentially 0, and we have 0.1 0 molar of this stuff, and this stuff is going to dissociate slightly in this backward direction to produce some amount of these two things. So it's going to look the same as what you're used to, but just a little bit backwards. And I'm keeping it in this form rather than just reversing the reaction because this is still using our K prime F value. Okay. We need to compute our K prime F now at the two different pHs, or conditional formation constant. So at pH 10, our K prime F, I'll just write K prime F at 10, that's going to be equal to Kf times our alpha. So that becomes, well, I'll just write it. So that's Kf times our alpha Y4 minus. So that is, let's see, 10 to the 10.65 multiplied by 0.3. So that's this value multiplied by this value, so Kf times that. That gives us a value of 1.34 times 10 to the 10. And then if we calculate our conditional at pH of 6, that's the same KF. It's the same expression, just to be consistent here. That's the same KF, 10.65, but in this case multiplied by this much smaller number, 1.8 times 10 to the minus 5, and that is 8.0 times 10 to the 5th. So conditional formation constants change by about 5 orders of magnitude simply by the pH, which makes sense because the concentration of Y4 minus at pH 6 is much, much lower, almost non-existent, compared with it being the dominant form at pH 10. I'll also mention that most protocols that utilize EDTA will have a buffered EDTA solution at pH 10 or 11, and the reason for that is because that sets Y4 minus as the dominant species in that case. Okay, so I can write up the actual equilibrium expression from our IE table. So that's the complex concentration over the free metal ion, which is what we're trying to compute, multiplied by Y4 minus here. So we can rewrite this then as K prime conditional formation constant equals our 0.10 minus x at equilibrium over x squared. And our Kf are these two values. So we could insert either one of these values to then compute the corresponding x. Okay, so we solve for x in this case at using the two different conditional formation constants, so the two different pHs, and we get at pH 10, 2.7 times 10 to the minus 6 molar, and x again is the free concentration of our calcium here, which means that you've got about 2.7 micromolar calcium floating around when you have 0.1 molar complex at pH 10, knowing at pH 10 that we have a lot more Y4 minus in the system. Then if you switch over to pH 6, you know that the fraction of Y4 minus goes down considerably, and our free calcium 2 plus concentration goes up by about 2 orders of magnitude to 3.5 times 10 to the minus 4. And that makes sense simply because there's less Y4 minus in the solution at that pH. Doesn't mean that calcium's not bound by other things, it is, but Y4 minus, because it's tetradentate and it's got the 4 minuses, it's the strongest binding, has the largest KF, and so the other species that are more present at lower pHs bind calcium less tightly, which means there's more of it freely floating around at that lower pH. Again, this is not a super important process for you to walk through. I'll walk you through why and how this is used in EDTA titrations, which is where we're going next with this. What this is mostly meant for you to understand is sort of the nature of what a free ion concentration is, and how that's modulated by pH here in the presence of EDTA, and how we generally are thinking about fraction and alpha and how that impacts KF and how we're using that. And so in that case, our conditional formation constant here is going to be our original formation constant multiplied by whatever the fraction of that species that's present in solution at that given time. And this isn't just relegated to EDTA, as we'll see. This is any complexation reaction. As long as we know the alpha for that species as a function of pH, then we can write up a single equilibrium expression, augment that concentration by using the alpha, and solve it explicitly. And that saves us a huge amount of time and hassle rather than having to solve everything systematically and simultaneously.